Hi everyone, it's a pleasure to be here to present our work, Time to Rethink the Design of Qi Standard, Security and Present Vulnerability Analysis of Qi Wireless Charging. My name is Yiwu, a third-year PhD student at the University of Tennessee, Knoxville. This is a collaborative work with my colleague Zhuo Hang, Nicholas, and my advisor Dr. Jian Liu. Wireless charging is making inroads in mobile and IoT industries as it offers promise of increased mobility and freedom while charging devices. Qi-certified wireless chargers for smartphones have become common in various locations, including home, workplace, hotels, airports, and coffee shops. Some companies also offer wireless charging EVs on the road today. With the ever-growing deployment of such wireless charging systems, it is essential to have a deep understanding of their vulnerabilities and the severity of the associated risks. In this paper, we explore the fundamental vulnerabilities of Qi wireless charging standard. Developed by WPC, Qi is the leading wireless charging standard for mobile devices. During power transfer, the primary coil generates an EM field that induces a current in the secondary coil to transfer energy. In addition, to allow the charging device to take control of the charging procedure, Qi specifies interoperable wireless power transfer and the data communication between the charger and the charging device. However, there exist two fundamental vulnerabilities. First, no encryption scheme has been deployed to secure the communication channel. Second, the requested power transfer density of the charging device is highly correlated with the device's activities, which opens opportunities for the adversary to detect and identify the charging device's activities using the Eavesdropping Qi messages. Based on these vulnerabilities, we propose two attacks. From the security perspective, we propose a hijacking attack where an adversary can hijack the communication channel and inject arbitrary malicious Qi messages to take control of the entire charging process. This can cause overcharging, undercharging, post-charging, which may reduce charging efficiency, battery life, and cause overheating and potentially cause an explosion. From the privacy perspective, we propose an eavesdropping attack where an adversary can eavesdrop the Qi messages and infer the smartphone's activities from a nearby hidden adversarial coil. The adversary can decode the Qi messages and identify whether the charging device receives a message notification, a phone call, or the screen is manually turned on by the user. Additionally, the adversary can further identify the specific app triggering the activities. Before I describe the text in detail, let me first give a brief introduction of Qi protocol. It contains four phases: selection, ping, IDNC, and PT, where the power transfer actually occurs. The Qi compliant transmitter is capable of communicating with the receiver and adjusting its transmit power density as requested by the receiver during Qi messages, particularly the control error messages. Qi messages are generated by the means of load modulation and composed of bypass encoded data bits with a period of 0.5 milliseconds. We assume the adversary has following capabilities. For hijacking attack, the adversary is assumed to be able to seamlessly place an adversarial coil between the charging pad and the charging device. For eavesdropping attack, the adversary can place the ultra-thin adversarial coil further away, such as hiding the coil underneath the surface on which the charger is placed. To verify whether the adversary is capable of injecting Qi messages, we conduct a preliminary experiment where the adversarial coil is stuck on the surface of the charger while a smartphone is being charged. Qi requires the perceived EM modulated signal to change significantly in the primary coil voltage, and we found that 80 kHz sine wave with 20 volts peak voltage on the adversarial coil can increase the primary coil voltage up to 3 volts. By switching off the signal, the primary coil voltage will return to its original Y level. To inject Qi messages, the adversary can follow the bypass encoding mechanisms to switch between the low and high states of the primary coil voltage. We first tried to inject 0101 signals in intervals to the normal Qi message transmission as shown in the figure. We can observe the bypass encoded 001 from the rectified coil voltage very clearly, which confirms our hypothesis. We then explore whether Qi messages can be snooped from the inductive voltage of a nearby hidden adversarial coil. In order to isolate Qi message relevant signals from the coil voltage, we apply a minimum average filter and a low-pass filter to smooth the signal and eliminate irrelevant frequency components. To derive the bypass encoded data bits, we further leverage the distance between two adjacent zero crossing points in the filtered signal. Two zero crossing points with a 0.5 millisecond distance indicates a 0 bit, while three zero crossing points with a 0.25 millisecond distance between each adjacent pairs represents a 1 bit. After obtaining the Qi messages, we test whether the occurrence of an activity have an impact on the control error sequence, and do different kinds of control error activities generate unique patterns on the control error values and the inductive voltage. The adversarial coil is hidden underneath the surface on which the charge is placed. The coil is connected to the probe of an oscilloscope. When an activity is triggered, as shown in the figure, we can observe that the values of the control error messages change greatly compared with no activity. To further verify the distinguishability of the inductive voltage on the adversarial coil during the phone activities, we measure the inductive voltage while the smartphone receives a cellular phone call and a WhatsApp phone call. We can see the voltage curves of the same activity have a very similar pattern, while the curves of different activities exhibit distinguishable patterns. These findings validate the hypothesis of our proposed attacks. We validate our hijacking attack under three scenarios: terminate charging process, reduce charging efficiency, and transfer excess power. In order to terminate the charging process, the adversary can modulate an EMP packet in the communication channel with an arbitrary value in the message byte. We can see as soon as the malicious EPT packet is injected, the charging process is terminated instantly in 0.05 seconds. In order to stop the charging process permanently, the adversary has to continuously inject EPT packets, in turn generating an inductive voltage on the primary coil voltage. To reduce charging efficiency, the adversary can flood a bunch of manipulated controller packets with a negative value in the communication channel. After we start injecting malicious packets with a control error value of -10, the primary coil voltage starts to linearly decrease and is reduced to only half of its original value within 2 seconds. To transfer excess power, we inject malicious control error packets with a positive value of 6. We can see after the malicious control error packets starts being injected, the primary coil voltage begins increasing and can nearly reach twice of its original value within 2 seconds. Existing studies have demonstrated that in a safe environment, the lithium battery keeps being overcharged. Terminal random wave would cause inducing the battery to vent with smoke, fire, or even an explosion. For the eavesdropping attack, we obtained a total of 128 time frequency features. To identify each activity, we apply a random forest classifier with feature selection. As shown in the table, we observe that our attack is able to distinguish different types of activities with a substantial degree of accuracy. For the tenfold cross-validation setup, the accuracy for all smartphones reached at least 95% accuracy. The reported classification accuracy, precision, and recall for all three phone models achieve more than 89% in both the tenfold cross-validation and the train test models for calling app classification, which are much higher than a random access attack. For the messaging app classification, even if these types of activities are the same, we still achieve a very high performance for the Samsung S7 and the LG G7 phones with accuracy over 84% and 89%, and the precision and recall over 86% and 90% respectively. This experimental results show that all these activities triggered by different apps exhibit unique and distinguishable patterns in the adversarial coil inductive voltage and its derived Qi control error sequence, which can put people's privacy at risk while recharging their smartphones wirelessly. We also analyze and evaluate several defense mechanisms for our attacks. For the hijacking attack, when there's a current flowing in the adversarial coil, the primary coil voltage will exhibit a different pattern due to the generated inductive power, as shown in the figure. Therefore, it's feasible to defend against the hijacking attack through detecting this external energy and swiftly terminate the charging process or reject the incoming messages once it's detected. Another possible approach is to defend against detect the incorrelation between the control message and the sudden rise of the primary coil voltage. For the eavesdropping attack, adding noises to the primary coil voltage will directly introduce additional distortion, which can cause the accuracy of messaging classification degree from 90% to 40%. Another way is to add electrical encryption mechanisms to protect the Qi messages. In conclusion, we conducted the first third study to explore the potential security and practical vulnerabilities of Qi web sharding. We demonstrated that due to the open propagation characteristic of EM signals, the Qi communication channel can be easily hijacked by injecting malicious Qi messages through stylus placement of an adversarial coil on the charger. Additionally, an adversary is capable of snowing Qi messages transmitted between the charger and the device to further detect and identify the ongoing activities of the smartphone being charged. Finally, we analyze and evaluate several defensive mechanisms against our attacks. Thanks for listening, and I'm ready to take any questions.